Hello class. At the end of our last video, we were able to determine that the pH of an intermediate species for leucine, where HA is equal to 0.050, was equal to 6.06. And we got there using this equation here, the concentration of hydronium, which is equal to the square root of an expression that contains Ka1, Ka2, Kw, and the concentration of the acid. So, with a pH of 6.06 and a hydronium concentration of 8.8 times 10 to the negative 7 molar, we are now able to actually calculate the rest of the species in solution using our Ka values. So, if we go on to the next page, we can use Ka1 to solve for H2A+. For Ka1, that's going to be equal to products over reactants, which is going to be equal to HA times hydronium divided by H2A+. We have our Ka value, we just calculated hydronium, and we had HA at the beginning of the problem. So H2A+ is going to be equal to HA divided by hydronium, multiplied by hydronium divided by Ka1 after we rearrange, and we get 0.050 times 8.8 times 10 to the negative 7 divided by our Ka 4.7 times 10 to the negative 3 is going to be equal to 9.4 times 10 to the negative 6 molar. We can also use Ka2 to solve for our conjugate base A-. So for Ka2, the products over reactants are equal to A- times hydronium divided by HA. If we rearrange, we get an expression for A- that's equal to Ka2 times HA divided by hydronium, which is equal to 1.8 times 10 to the negative 10 times 0.05, all divided by 8.8 times 10 to the negative 7, which ends up being equal to 1 times 10 to the negative 5th molar. Now we're going to take the expression for H3O plus for our intermediate form and simplify it, which is often quite possible. So our hydronium concentration is equal to the square root of Ka1 times Ka2 times HA plus Ka1 times Kw divided by Ka1 plus HA. Now we're going to make a few assumptions here that's going to allow us to simplify this significantly. First, if we take a look at what value arises when we take 4.7 times 10 to the negative 3, our Ka value, and multiply it by our Kw value, 1 times 10 to the negative 14, we get a value that's equal to 4.7 times 10 to the negative 17. That's very, very small. Our Ka1 is often going to be quite small, but when you multiply it by Kw, you get a value that's extremely small, a very large negative exponent. So that whole expression added to the previous, Ka1 times Ka2 times HA, you can imagine is going to have very little impact on the numerator, so we can cancel it and get rid of it. Further, when we compare Ka1 to HA, generally Ka1 is going to probably be a lot smaller than HA. In our situation, we have 4.7 times 10 to the negative 3 is less than our HA concentration, 0.050. In a lot of situations, there's going to be a greater difference here. This is about a factor of 10, so it's not that different, but it's going to allow us to make an assumption. Ka1 is smaller, can ignore. This works a lot better for a greater difference. But for the purposes of this problem, we're going to say that, yes, we can ignore this. Once that happens, our expression simplifies down to hydronium is equal to the square root of Ka1 times Ka2 times HA divided by HA. We no longer have any addition or subtraction in our numerator or denominators. We just have multiplication. That then allows us mathematically to cancel HA. So they cancel, and they're now gone. We are then left with a hydronium expression that's equal to the square root of Ka1 times Ka2. Not bad. So we take our hydronium concentration, which is equal to the square root of Ka1 times Ka2, and that equals 9.2 times 10 to the negative 7. If we go back and we can compare that to our hydronium concentration that we calculated last time, 8.8 times 10 to the negative 7, they are pretty close. So that assumption is not that bad. Had there been a greater difference in Ka1 and HA for this part of our simplification, these values would probably be a lot closer. So we can take our simplified hydronium equation and we can derive it for pH. So our hydronium concentration is equal to the product of Ka1 times Ka2, all raised to the power of 1/2. That's just this simplified down to creating this square root as an exponent. If we take the negative log of everything, we get the negative log of hydronium is equal to, using our logarithmic values, negative 1/2 times the sum of log of Ka and the log of Ka2. We can then distribute the negative sign on the right side of the expression, and we get that 1/2 times the negative log of Ka plus 1/2 times the negative log of Ka2. We now have negative logs in each part of our equation, and those simplified to p's. So the negative log of hydronium is pH, the negative log of Ka1 is pKa1, and the negative log of Ka2 is pKa2. So we now have an expression that for pH that's just equal to 1/2 of pKa1 plus 1/2 of pKa2, and if we factor out a 1/2, we get the pH is equal to 1/2 times pKa1 plus pKa2, which is essentially the average of pKa1 and 2. We can use this simple expression to estimate a pH. If we have to calculate it with a lot of high degree of precision, we must use our other expression. But if the word problem says the word estimate, you are allowed to use this equation. So let's take a look at how might that happen. In example 13, we have potassium hydrogen phthalate, KHP, which is a salt of intermediate form phthalic acid. Calculate the pH of both 0.1 molar and 0.01 molar of KHP. KHP is this intermediate species, which we can simplify and call it HA. So if we estimate our pH, that's going to be equal to the 1/2 times pKa1 plus pKa2, which are both provided to us. So 2.950 plus 5.4005, we get a pH that's estimated to be 4.18. What's really interesting about this is that it is not dependent on any of the concentrations of anything in solution. It's just the pKa's around the species that you're focusing on. So for which concentration is this estimation most likely true? Well, when we compare 0.1 and 0.01, it is most likely true for 0.1. Why is that? Well, we want the denominator in our first assumption to be as great of a difference as possible. So if HA is really, really large, and Ka1 is really, really small, that increases the likelihood that we can cancel out that Ka1. So in some situations, Ka1 is really, really small, but the larger the HA, the better. So down here, we are simply going with the larger HA value. Now, we can continue and calculate from hydronium. So here we have our hydronium species. That's equal to our expression here. Ka1 times Ka2 times HA plus Ka1 times Kw divided by Ka plus HA. So we have our Ka values from previously. Those were provided in the problem. And if we take 10 raised to the negative pKa's, we can get our Ka values. So Ka1 is 10 raised to the negative pKa1, and that's 1.12 times 10 to the negative 3. Ka2 is 10 raised to the negative pKa2, and that equals 3.91 times 10 to the negative 6. So if we calculate our hydronium for when we have an HA molarity that's 0.10, we end up calculating that 6.58 times 10 to the negative 5th molar is equal to our hydronium concentration, and that our pH is equal to 4.18. If we compare the 4.18 that we just calculated using this expression to the previous page where we estimated the pH, turns out they're the same. So they are very, very close, or if not the same, when we have a large value of HA. However, if we were to calculate hydronium using this equation for an HA that's equal to 0.010, we would end up with a hydronium that's equal to 6.28 times 10 to the negative 5th molar, which gives us a pH of 4.2. So the smaller HA gets, the more the pH estimation drifts away from the actual. So the actual is 4.20, but previously that would just be estimated to, again, be 4.18, because the estimation is independent of concentration. Let's now take a look at a triprotic species, for example, phosphoric acid. So the fully protonated form is H3A, and that gets deprotonated by Ka1 to make H2A minus plus one equivalent of hydronium. H2A minus is an amphoteric species, which is acidic and basic. So H2A minus can get deprotonated again via Ka2 to form Ha2 minus. Ha2 minus can also act as an acid or base and can be deprotonated by Ka3 to form A3 minus, which is our base, our fully deprotonated species. Over here on the right, we've listed that each of these reactions can be described as Ka1, Ka2, and Ka3. Going in the reverse direction, we get Kb's. We start at A3- and we get protonated by Kb1 to form Ha2-. Ha2- gets protonated by Kb2 to form H2A-, and H2- gets protonated by Kb3 to form acid, the fully protonated species H3A. Those Kb values are shown here. Ka1 is associated with Kb3, Ka2 is associated with Kb2, and Ka3 is associated with Ka1. When you multiply each of these together, the relationship holds that they are each equal to Kw. So, our fully protonated form we can treat as a monoprotic acid. We have two intermediate forms which can be treated using our hydronium expression for an intermediate form, and A3- can be used as our fully basic monobasic species. So even though we have added an additional acidic proton, the way that we treat each of these species stays the same. Our fully protonated version is our acid. We can treat that as a monoprotic acid. Our fully deprotonated we can treat as a monoprotic base. Everything in the middle gets that special equation for the intermediate form, or you can estimate its pH. So let's take a look at what happens here. H3A is our fully protonated form. We can consider that as a monoprotic acid. Ka1 is associated with that deprotonation and is equal to H2A- times hydronium divided by H3A. At equilibrium, we would have x squared divided by H3A minus x. For H2A, that's an intermediate form. So hydronium is going to be equal to Ka1 times Ka2 times H2A minus plus Ka1 times Kw divided by Ka plus H2A minus. We can estimate the pH at this intermediate form using this expression, where pH is equal to 1/2 of pKa1 plus pKa2. Ha2- is our second intermediate form. That can be treated using the following equation, where H3O- is equal to the square root of Ka2 times Ka3 times Ha2- plus Ka2 plus times Kw divided by Ka2 plus Ha2-. The pH can be estimated at this point using 1/2 times pKa2 plus pKa3. So to go back up, we can see that H2A- is this intermediate form, which can be deprotonated or protonated. So the Ka2 and Ka1 are around this species. Ha2- is between Ka2 and Ka3. And finally, our A3- can be treated as monobasic. A3- would then react with water to form Ha2- and hydroxide. Remember, once we are under basic conditions, there's no more hydronium present. For this expression, we can describe it as Kb1 being equal to products over reactants. Ha2- times hydroxide divided by our fully deprotonated species, A3-. We would need the Kb to solve here, and we could use the expression from the autoionization of water that Ka3 times Kb1 is equal to Kw, and we would be able to solve for Kb1. We're now going to move on and discuss something called the principal species. And when faced with the problem of identifying which species of acid, base, or intermediate is predominant under given conditions, the predominant species can be determined by comparing pK values to pH. What we're interested in with the principal species is which compound has the highest concentration at a given pH. And we can compare using pKa's. Because once we have polyprotic species, we have a lot of compounds that are in solution and are in equilibrium with one another, so it can be difficult to figure out which one of which there is the most. So for example, we're going to take a look at a principal species of a monoprotic acid. For this example, benzoic acid. So if we are at a pH that is equal to 4.20, and our pKa for this reaction is also 4.20, what ends up happening is that A- and HA end up in a 1-to-1 molar ratio. You have 50% of each, because the pH is equal to pKa plus the log of A- over HA. We know this from the Henderson-Hasselbalch equation. So then 4.20 is equal to 4.20 plus the log of A- over HA. So we have 0 is equal to the log of A- over HA. In that situation, the log of 1 must equal 0, so A- and HA must be equal to one another. So A- and HA are in a 1-to-1 ratio, so you end up having 50% of each. Now, when you have a principal species of a polyprotic system, you must use all of the Kas that are relevant. So here we're going to use arginine, where we have H3 arginine 2+, gets deprotonated by pKa1 to form H2 arginine plus. It can get deprotonated by pKa2 to form H arginine, and can get deprotonated by pKa3 to form arginine minus. So this is a triprotic species. At pH of 8.99, what are the dominant species in solution? So at pH of 8.99, we are exactly at pKa2. This is going to be similar to the situation with benzoic acid above. So at a situation where pH is equal to pKa, there is a 50-50 mixture of the surrounding species. So if we're at a pH that is equal to this pKa, then we have a 50-50 mixture of H2 arginine and H arginine. At a pH of 10, what is the predominant species? At a pH of 10, the dominant species is between pKa2 and pKa3. pKa2 is 8.99, pKa3 is 12.1. So at a pH of 10, we're between those two values. So we can assume that the greatest amount of species present is going to be H arginine, which we have identified here. Next, at what pH is there the most H2 arginine plus in solution? So we're trying to figure out at what pH do we have the most of this H2 arginine? Turns out it's halfway between the pKa values on either side. And the reason for that is you can sort of think of a bell curve between the two Ka values. So at Ka1, we have a 50-50 mixture of H2 arginine and the protonated species. At Ka2, we have a 50-50 mixture of H2 arginine and the deprotonated species. But when we're right in the middle, we have the most amount of H2 arginine plus in solution that we can possibly have. So the most H2 arginine plus is present at the midpoint between pKa1 and pKa2. So at what pH do we find that? pH is equal to 1/2 of pKa1 plus pKa2, which is 1/2 of 1.82 plus 8.99. Turns out is at a pH of 5.41. We can now look at predominant species in a form of this graph here, or chart here, where we have each of the protic species getting deprotonated along K values, and you can think of each of these little zones as being sort of a bell curve. And when you're right at the midpoint of each one of them, you have the most of that component in solution.